Search algorithms are one of the most important areas of artificial intelligence. In this video, I will explain all about the search algorithms in AI. Artificial intelligence is basically the replication of human intelligence through computer systems or machines. It is done through the process of acquisition of knowledge or information and addition of rules that are used by information. And using these rules, it derives conclusions, that is reasoning, and do self-corrections. Artificial intelligence is the study of building agents that act rationally. Most of the time, these agents perform some kind of search algorithm in the background in order to achieve their task. Searching is the universal technique of problem solving in AI. Search in AI is the process of navigating from a starting state to a goal state by transitioning through intermediate states. Algorithms used in searching are known as search algorithms. A start state, search space, and goal state makes up a search problem. Through the evaluation of scenarios and options, search algorithms assist AI agents in achieving the goal state. The search algorithms help you to search for a particular position in single-player games such as tile games, Sudoku, crossword, etc. Through a series of steps that change the starting state into objective state, the algorithm will offer the search results. So without these algorithms, AI programs and computers are unable to do searches and come up with workable solutions. So before we begin the session, let's look at the agenda. First, we will understand what is search algorithm. Then we will talk about the importance of search algorithm. Next, we will see the search algorithm's infrastructure. And then we will see how the search algorithm works. And once this is done, we will look how to measure the problem solving performance. Then we move on to the classification of search algorithm in detail. In that, we will identify the popular search algorithms in AI. And finally, we will end the session by looking after the applications of search algorithms. Now let's move on and understand what are search algorithms in AI. The solution to a search problem is a sequence of actions called the plan that transforms a start state into a goal state. And this plan is achieved through search algorithms. Search algorithms are algorithms that help in solving search problems. Searching is a step-by-step procedure to solve a search problem in a given search space. A search problem can have three main factors. That is the search space, start state, and goal test. A state space or search space is a set of possible states where you can be. And start state is a state where the search begins. Goal test is a function that monitors the current state and indicates if the goal state has been attained or not. Okay, having formulated some problems, we now need to solve them. A solution is an action sequence, so search algorithms work by considering various possible action sequences. The possible action sequences starting at the initial state form a search tree. A tree representation of a search problem is called a search tree. The root of the search tree is the root node which corresponds to the initial state. The branches are the actions and each node in the tree corresponds to the states in the state space of the given problem. And the given diagram shows the first few steps in growing the search tree for finding a route from Arad to Bucharest. The root node of the tree corresponds to the initial state. Here it is Arad. And the first step is to test whether this is a goal state. Then we need to consider taking various actions. We do this by expanding the current state, that is applying each legal actions to the current state, thereby generating a new set of states. In this case, we add three branches from the parent node. Here the parent node is Arad, leading to three new child nodes. And the child nodes are CPU, Timisoara, and Zerend. Now we must choose which of these three possibilities to consider further. And this is the essence of search. We will follow up one option and put the others aside for later if the first choice does not lead to a solution. Suppose we choose CPU first, then we check to see whether it is a goal state or not. And then we expand it to get to Arad, Fagaras, Oradia, and Rimniku-Velcha. We can then choose any of these four and go back and choose Timisoara or Zerend. Each of these 6 nodes is a leaf node, that is a node with no children in a tree. The set of all leaf nodes available for expansion at any given point is called the frontier. In this diagram, the frontier of each tree consists of those nodes with bold outlines. The process of expanding nodes on the frontier continues until either a solution is found or there are no more states to expand. All search algorithms share this basic structure and they vary primarily according to how they choose which state to expand next, the so-called search strategy. And so far we have seen what is search algorithm. Next I will explain how and why the search algorithms are important in artificial intelligence. Basically, search algorithms enhance the solving of problems in artificial intelligence through logical search mechanisms such as problem definition, actions, and search space. So it is important in solving problems. And next, it is important in search programming because many AI tasks can be programmed in terms of search, which enhances the formulation of solution to a given problem. And we know that search algorithms enhance the effective operation of goal-based agents. So these agents solve the problem by searching for the most ideal series of actions that can provide the best solution to a problem. Search algorithms support the operation of production systems in AI. A production system is a type of cognitive architecture for implementing search algorithms and simulating human problem-solving abilities. And the production system is popularly known as production rule system, which is a kind of cognitive architecture that is used to implement the search algorithms and replicate the human problem-solving skills. This problem-solving knowledge is encoded in a system in the form of little quanta, popularly known as productions. It consists of two components, that is rule and action. Rules recognize the condition, and the action part has the knowledge of how to deal with the condition. And these are the systems that support AI applications through the use of rules and procedures for implementing them. Production system use the search algorithm to search for the sequence of rules that result in desired action. Also, these algorithms are important in neural network systems. The neural networks are the computing systems that consist of interconnected nodes, a hidden layer, an input layer, and an output layer. A neural network is a method in artificial intelligence that teaches the computer to process data in the way that is inspired by the human brain. And it is a type of machine learning process called deep learning that uses the interconnected nodes or neurons in a layered structure that resembles the human brain. These networks create an adaptive system that computers use to learn from their mistakes and improve continuously. Thus, the artificial neural network attempts to solve complicated problems like summarizing the documents or recognizing the faces with greater accuracy. And so far, we have seen the importance of search algorithms in artificial intelligence. Now, let's move further and understand the infrastructure for search algorithms. The search algorithms require a data structure to keep track of the search tree that is being constructed. For each node of the tree, we have a structure that contains 4 components, which includes state, parent, action, and pathcast. A state is a potential outcome of any problem, and state contains all the information necessary to predict the effect of an action to determine if it is a goal state. And we know that state space is a set of all configurations that a given problem and its environment could achieve. And each configuration is called a state and contains 2 information, that is static information and dynamic information. The static information is often extracted and held separately. For example, the knowledge base of an agent. And the dynamic information which changes between the states. This is held in the problem representation of an agent. For example, chess has too many states and a dice has 6 states. And the Google Map route finder problem have number of states depend on the task. A parent node is a node in a search tree that generates a node. A parent node is a node that produces the child node. And the action is what we apply to the parent node to generate a node. A pathcast is a function that assigns a numeric value to each path. Traditionally, this function is denoted by g of n. In this figure, you can see the nodes are the data structure from which the search tree is constructed. Each has a parent, state, and various bookkeeping fields. And arrows points from child to parent. The node data structure is depicted in this figure. And you can notice how the parent pointers string the nodes together into a tree structure. These pointers also allow the solution path to be extracted when a goal node is found. A node is a bookkeeping data structure used to represent the search tree, whereas a state corresponds to a configuration of the world. Now let's move on and understand how the search algorithm works. We know that artificial intelligence is made possible through AI agents. And these agents perform tasks towards achieving a certain goal and establish the actions that can result in a desired goal. And thus the series of these actions provide the solution to the problem. The AI agents find the best solution for the problem by searching all the possible alternatives or solutions. And this process of searching is done using the search algorithms. Search algorithms work in 2 main phases, namely defining the problem and searching in search space. Before formulating a problem, various factors need to be defined to enable the search algorithms to perform the required course of action. Defining these factors provide the basis for searching and providing a solution. The following are the factors that need to be defined. First, the initial state. This is the start state in which the search starts. And next, the state space. These are all the possible states that can be attained from the initial state through a series of actions. And we know that actions are the steps, activities, or operations undertaken by AI agents in a particular state. The goal test is the endpoint or the desired state. And next we have the goal test. This is a test conducted to establish whether the particular state is goal state. And finally we have path cost. This is the cost associated with a given path taken by the agents. After defining the factors, the agent uses the search algorithms to provide the search in a search space. A search space is an abstract configuration that consists of search tree of possible solutions. A search tree is used to configure the series of actions. The initial state is configured as root of the search tree, and the branches are the actions, while nodes are the outcomes of the actions. When we have a given problem in AI, the search algorithm will identify the initial state, state space, actions, goal state, and pathcast. From the initial state, a series of actions will be performed, and the search algorithm will search for a goal state. For every state attained by AI agents, the search algorithm will conduct a goal test to establish whether the state is desired state. If a particular state attained by AI agent is not a goal state, then the search algorithm will continue searching until the goal state is obtained. And this is how the search algorithm works. Before we move on to the types of search algorithm, let's see how can we evaluate the algorithm performance. We can evaluate an algorithm's performance in 4 ways. And these are the 4 essential properties of search algorithm to compare the efficiency. The first property is completeness. A search algorithm is said to be complete if it provides a solution for a given input when there exists at least one solution for the input. That is, it must guarantee to return a solution if at least any solution exists for any random input. And next, the optimality. Search algorithms are also characterized by optimal solutions. These are the best solutions given by the search algorithm at the lowest path cost. That is, if a solution found for an algorithm is guaranteed to be the best solution at lowest path cost among all other solutions, then such a solution is said to be an optimal solution. And next, the time complexity. These algorithms will take a maximum time to accomplish a task or provide a solution. The time taken is usually based on the complexity of a task. The time complexity is a measure of time for an algorithm to complete its task. So the time complexity is how long does it take to find a solution. And finally, we have space complexity. The space complexity is the maximum storage space required at any point during the search. They have a maximum memory or storage space needed when conducting a search operation. This memory is also based on the complexity of the task. So the space complexity is how much memory is needed to perform a search. Time and space complexity are always considered with respect to some measure of the problem difficulty. In the theoretical computer science, the typical measure is the size of the state space graph, and which is denoted as V plus E, where V is set of vertices or the nodes in the graph, where E is set of edges or links that connects the nodes. This is appropriate when a graph is an explicit data structure that is an input to the search program. An example of this is map of Romania. And we know that in AI, the graph is often represented implicitly by the initial state, actions, and transition model and is frequently infinite. For these reasons, complexity is expressed in terms of 3 quantities. And first we have branching factor, which is denoted as B. This branching factor is the maximum number of successes of any node. And the next quantity is depth, which is denoted as D. The D is the depth of the shallowest goal node. That is the number of steps along the path from root. And the last quantity is the maximum length of any path in the state space, which is denoted as M. So we can say the time is often measured in terms of number of nodes generated during the search, whereas space is measured in terms of maximum number of nodes stored in a memory. So the time and space complexity for search on a tree or for a graph, the answer depends on how redundant the path in the state space are. And so far we have seen the properties of search algorithm. Next we move on to the types of search algorithm. There are 2 types of search algorithms, uninformed and informed. Based on the search problem, we can classify the search algorithms into 2 types, uninformed search or blind search and informed search or heuristic search. Uninformed search is a class of general purpose search algorithm which operates in brute force way. And these uninformed search algorithms do not have any additional information about the state or the search space other than how to traverse the tree. So it is called a blind search. All they can do is generate successes and distinguish a goal state from non-goal state. And these algorithms can further be categorized into following algorithms: breadth first search, depth first search, uniform cost search, depth limited search, iterative deepening depth first search, bidirectional search. In breadth first search, the tree or a graph is traversed breadthwise. That is, it starts from a node called search key and then explores all the neighboring nodes of the search key at the depth first and then moves to the next level. It is implemented using the queue data structure that works on the concept of first in, first out, and it is a complete algorithm as it returns a solution if a solution exists. The time complexity for breadth first search is B to the power D. where B is the branching factor, which is an average number of child nodes for any given node, and D is depth. The disadvantage of this algorithm is that it requires a lot of memory space because it has to store each level of nodes for the next one. It may also check duplicate nodes. And here is an example. If the search starts from the root node A to reach the goal node G, then it will traverse in the order from A, B, C, D, and G. It traverses level wise, that is, it explores all the shallowest node first. And next, depth first search. In depth first search, the tree or a graph is traversed depth wise. That is, it starts from a node called search key and then explores all the nodes along the branch, then backtracks. It is implemented using a stack data structure that works on the concept of last in first out. The time complexity for depth first search is b to the power d, where b is the branching factor, which is the average number of child node for any given node, and d is depth. It stores the node linearly, so less space is required. The major disadvantage is that this algorithm may go in infinite loop. And here is an example for depth first search. If the search starts from root node A to reach goal node G, then it will traverse A, B, D, G. It traverses depth-wise, that is, it explores all the deepest node first. And next we have uniform cost search. Uniform cost search is different from both DFS and BFS. In this algorithm, the cost comes into the picture. And here there may be different paths to reach the goal, so the path with the least cost is optimal. And here the cost is calculated as a cumulative sum of all the cost. And it traverses the path in the increasing order of cost. It is similar to the breadth first search if the cost is same for each transition. The uniform cost search algorithm is used for visiting the weighted tree. The main goal of this algorithm is to fetch the goal node and find the true path, including the cumulative cost. The expansion takes place on the basis of cost from the root, and this algorithm is implemented using a priority queue. This algorithm does not care for the number of steps, so it may end up in infinite loop. The time complexity for this algorithm is denoted as b to the power d, where b is the branching factor, which is the average number of child nodes for any given node, and d is depth. And here is an example for uniform cost search algorithm. In this figure, you can see the search starts from the node A of a graph to reach the goal node G as it traverses from A, C, and G1. So the cost will be 3. We can say the uniform cost search is optimal algorithm as it chooses the path with the lowest cost only. And next we have depth limiter search algorithm. This algorithm is similar to depth first search with a predetermined limit. Depth limited search can solve the drawback of infinite path in the depth first search. We denote this limit by L, and thus this provides a solution to the infinite path problem that is originated earlier in the DFS algorithm. And thus the depth limited search can be called as an extended and refined version of DFS algorithm. To avoid the infinite loop status while executing the codes, the depth limited search algorithm is being executed into finite set of depth called depth limit. And in this algorithm, the node at the depth limit will be treated as it has no successor nodes further. Depth limited search can be terminated with two conditions of failure: standard failure value and cutoff failure value. The standard failure value indicates that the problem does not have any solution. And next, the cutoff failure value. It defines no solution for a problem within a given depth limit. And if we fix the depth limit to 2, the DLS can be carried out similarly to the DFS until the goal node is found to exist in the tree search domain. And this is the algorithm of the example. First, we start with finding and fixing a start node. Then we search along with the depth using the DFS algorithm. Then we keep checking if the current node is goal node or not. If the answer is no, then we do nothing. If the answer is yes, then we return. Now we will check whether the current node is lying under the depth limit specified earlier or not. If the answer is no, then we do nothing. If the answer is yes, we will explore the node further and save all of its successors into a stack. Now call DLS recursively for all the nodes of the stack and go back to step 2. Now look at this example. In this we have a tree with 6 nodes. Our target node is 5. For this example, we will use the level limit of 2 as we traverse the tree. We use a visited array to mark off nodes we have already traversed through. So this keeps us from visiting the same node multiple times. Now let's see how it works. We follow the normal DFS and start with the root node 1 at level 0. We mark it visited and add its child nodes 2 and 3 to the stack. And we increment our level by 1. Node 2 is at top of our stack. We add its children nodes 4 and 5 to our stack. And now we increment our level by 1. So our level counter is now 2. Now node 4 is on top of our stack. We can add its child node 6 to our stack. And doing this will exceed our level counter, so ignore node 6. Now node 5 is on top of our stack. but it has no children to append to our stack. Now node 5 is our desired result, so algorithm stops. And you can see we ignore node 6 as it was below our level limit. So what would happen if our desired node is 6? And this is known as cutoff failure. That is, our target exists, but it is too deep for us to traverse. For example, if our level limit is 3 and our desired node was 7, it could traverse the whole tree without finding the result. And that would be the standard failure. And the time complexity for DLS is b power d, where b is the branching factor, which is the average number of child nodes for any given node, and d is the level limit. And the next algorithm is iterative deepening depth first search. This algorithm is combination of DFS and BFS. This search algorithm finds out the best depth limit and does it by gradually increasing the limit until the goal is found. That is, this algorithm performs the depth first search up to a certain limit, and it keeps increasing the depth limit after each iteration until the goal node is found. This search algorithm combines the benefits of BFS fast search and DFS memory efficiency. And this algorithm is very useful when the search space is large and depth of the goal node is unknown. The time complexity of IDDF is b to the power d, where b is the branching factor, which is the average number of child nodes for any given node, and d is the level limit. And this algorithm repeatedly applies the depth limited search with the increasing limits. It gradually increases the limits from 0, 1 and up to d until the goal node is found. And the nodes at the bottommost level, which would be the level d, and it will be expanded exactly once. Whereas the nodes on the level d-1 will be expanded twice. And the root node of our tree will be expanded d plus 1 times. And this summation will result in the time complexity, that is b to the power d. And we use this algorithm when we do not know the depth of our solution, and also when we have to search for a very large state space. And this algorithm is also used as a slightly slower substitute for BFS if we are constrained by memory or space. This algorithm terminates in the following two cases. It terminates when the goal node is found, or it terminates when the goal node does not exist in the graph or tree. Let's understand this algorithm with an example. From the figure, we know that the depth is 4. In this example, we consider the tree as a finite tree, while we can consider the same procedure for the infinite tree as well. And we knew that in the algorithm of IDDFS, we first do the DFS till the specified depth, and then we increase the depth at each loop. And this special step forms the part of DLS or depth limited search. Thus, the following traversal shows the IDDFS search. From the figure, let's consider the goal node be G and the start state to be A. We perform our IDDFS from the node A. In the first iteration, it traverses only node A at level 0. Since the goal node is not reached, we expand our nodes, go to the next level, that is level 1, and move to the next iteration. Then in the next iteration, we traverse the node A, B, and C. Even in this iteration, our goal node is not reached, so we expand our node to the next level, that is to the level 2, and the nodes are traversed from the start node or from the previous iteration, and expand the nodes A, B, C, and D, E, F, G. Even though the goal node is traversed, we go through for the next iteration, and the remaining nodes A, B, D, H, I, E, C, F, K, and G are explored. That is, we are applying both BFS and DFS. And finally, we find the goal state in this iteration. This is the implementation of IDDFS algorithm. And the main disadvantage of this algorithm is that it repeats all the work from the previous phase. Next, we have bidirectional search. The bidirectional search algorithm runs two simultaneous searches, one from the initial state called forward search and other from the goal node called backward search. And this search algorithm replaces one single search graph with two small subgraphs. So here we have two searches. One starts from the initial vertex and other starts from the goal vertex. The search stops when these two graphs intersect each other. Heuristic refers to the concept of finding the shortest path from the current node in a graph to the goal node. The search always takes the shortest path to the goal node, and this principle is used in the bidirectional heuristic search. The only difference is being the two simultaneous searches, that is from the initial point and from the goal vertex. So the main idea behind the bidirectional search is to reduce the time taken for the search drastically. And this is done when the both searches happen simultaneously from the initial node and the goal node, intersecting somewhere in between the graph. Now the path traverses through the initial node through the intersecting point to the goal vertex is the shortest path found because of this search. So this is the shortest path and found in fraction of time taken by the other search algorithm. The bidirectional search is categorized into two types, which is front to back and front to front. And in this search, two heuristic functions are needed. First is the estimated distance from the node to the goal state using forward search. and the second is the node to the start state using reverse action. Here h is calculated in this algorithm. It is a heuristic value which is the distance between the node n to the root of the opposite search tree S or T. In front to front, distance of all nodes is calculated, and h is calculated as the minimum of all heuristic distances from the current node to the node on the opposing fronts. And let's see an example for bidirectional search, and this figure gives a clear-cut idea of how BSS is executed. We have the node 1 as a start state and node 16 as a goal node. And this algorithm divides the search tree into two subtrees. So from the start node 1, we do the forward search, and at the same time, we do the backward search from the goal node 16. The forward search traverses nodes 1, 4, 8 and 9, whereas backward search traverses through the nodes 16, 12, 10 and 9. We can see both forward and backward search meets at the node 9 called intersection node. So the total path traced by the forward search and the path traced by the backward search is the optimal solution. And this is how the BS algorithm is implemented. Talking about the advantage of BS algorithm, it is fast as well as requires less memory. And next, the disadvantage of BS algorithm. The implementation is difficult. Also, one should know the goal state in advance. The time and space complexity of this algorithm is b to the power d by 2 because we execute two search operations. So for each search, the total complexity would be b power d by 2 plus b power t by 2, which is far less than b power d. And so far we have seen the uninformed search strategies. Each search algorithm is no less than the other, and we can use any one of the search strategies based on the problem. The term uninformed means that they do not have any additional information about the state or the state space. So we can say the uninformed algorithm is an algorithm that does not have any prior knowledge or heuristics to solve a problem. And next we move on to the informed search. In uninformed search algorithm, we do not have any additional information about the search space. But in the informed search, we have array of knowledge. And knowledge like how far we are from the goal node and the path cast and how to reach the goal node. That is, this kind of algorithm will have a domain knowledge. That is, it has the problem description as well as the extra information. And this algorithm is more useful when the search space is large. Also, they are better at solving complex problems. And this informed search is also called a heuristic search. Heuristic is a function which finds the most promising path. That is, heuristic is a way which might not always be guaranteed for the best solution, but guaranteed to find the good solution in a reasonable time. The heuristic function takes the current state of an agent as its input and produces the estimation of how close agent is from the goal. And it is represented by h of n, and it calculates the cost of an optimal path between the pair of states. So the h of n is estimated cost of the cheapest path from the start node to goal node. The value of heuristic function is always positive. The heuristic evaluation function is given by h of n less than or equal to h star of n. H of n is heuristic cost and h star of n is the estimated cost. Hence, the heuristic cost should be less than or equal to the estimated cost. Before moving on to the types of informed search, let's understand what is pure heuristic search is. Pure heuristic search is the simplest form of heuristic search algorithm. It grows nodes according to their heuristic value. The classic example of heuristic search method is traveling salesman problem. In heuristic search, two lists is created, open list and closed list. The open list is for new but unexpanded nodes and the closed list for expanded nodes. For every iteration, the node with the smallest heuristic value is expanded and all its child nodes are expanded and added to the closed list. A heuristic function is then applied to the closed list and the node with the shortest path is saved and rest are dispersed. This algorithm continues until the goal node is found. The informed search algorithm is classified into two main types, greedy best first search and A-star search. Best first search algorithm or greedy algorithm. In this algorithm, we expand the closest node to the goal node. The closeness factor is roughly calculated by the heuristic function h of n. Using the technique of both DFS and BFS, the greedy search at its core uses the best path from the current state to find the shortest path. The evaluation function is equal to the heuristic function, which is denoted by f of n is equal to h of n, where h of n is the estimated cost from the node n to the goal node. The greedy best first search algorithm is implemented by the priority queue. This algorithm is more efficient than BFS and DFS algorithm, but it can behave as an unguided depth first search in the worst case scenario. Also, it can get stuck in a loop as DFS. So this algorithm is not optimal. Let's see an example for greedy best first search algorithm. First, initialize the tree with the root node being the start node in the open list. If the open list is empty, return a failure. Otherwise, add the current node to the closed list. Next, remove the node with the lowest heuristic value from the open list for exploration. If a child node is the target node, return a success. Otherwise, if the node is not either in open or closed list, add it to the open list for exploration. And in this example, we are finding the path from P to S. The cost is measured strictly using the heuristic value. C has the lowest cost of 6. Therefore, search will continue. From C, we move to U because the node U has the lowest cost compared to M and R. So the search will continue by exploring U. Finally, S has the heuristic value of 0 since that is the target node. The total cost for the path from P to C, from C to U, and U to S evaluates to 11. The potential problem with this algorithm is revealed by the path from P to R, R to E, and E to S having the cost of 10, which is lower than the P to C, C to U, and U to S. And this algorithm ignores this path because it does not consider the edge weights. The worst case time and space complexity of this algorithm is B to the power D, where B is the branching factor and D is the depth of the search space. And next, A star search algorithm. It is a searching algorithm that is used to find the shortest path between the initial node and a final point. Initially, it was designed as a graph traversal problem. It searches for the shortest path first and then makes the algorithm optimal and complete. An optimal algorithm will find the least cost outcome for a problem, while complete algorithm will find all the possible outcome of a problem. And another aspect that makes A star so powerful is it uses the weighted graphs in its implementation. The weighted graph uses the numbers to represent the cost of each path, which means an algorithm can take the path with the least cost and find the best route in terms of distance and time. The major drawback of this algorithm is its time and space complexity, because it takes larger amount of space to store all possible paths and lot of time to find them. And this algorithm is known form of BFS algorithm. Also, it combines the features of uniform cost search and greedy best first search. And the total cost is denoted by f of n, which is the sum of g of n and h of n, where g of n is cost in uniform cost search, h of n is cost of greedy search. So we evaluate the nodes by combining g of n and h of n. And g of n is the cost to reach the node n, that is, it gives the path cost from the start node to node n. And h of n is the cost to get from the node n to goal node. It is the estimated cost of cheapest path from node n to goal node. And f of n will give the estimated cost of cheapest solution through n. H of n is known for forward cost, while g of n is backward cost. The forward cost estimates the distance between the current node and the goal node. The backward cost is used to establish the overall cost between the node and the root node. And it is implemented using priority queue by increasing f of n. There is one formula that you need to remember, which is the heart and soul of this algorithm. F is equal to g plus h. So what are these three variables and why they are so important? Let's understand now. F is the parameter of A star, which is the sum of the other parameters g and h, and it is the least cost from one node to the next node. This parameter is responsible for helping us to find the most optimal path from the source to destination. And next, g, which is the cost of moving from one node to other node. This parameter changes for every node as we move up to find the most optimal path. And h is the heuristic or estimated path between the current node to the destination node. This cost is not actual, but in reality it is a guess cost that we use to find which could be the most optimal path between our source and destination. Now let's see a simple example to understand how this algorithm works. Suppose we have a small graph with vertices S, A, B and E, and here S is the source and E is the destination. And remember, the cost to enter the source and destination is always 0. And the heuristic values are S equals 5, A equals 4, B equals 5 and E equals 0. Let's use the formula and calculate the shortest path from source to destination now. There is F equals G plus H, where G is the cost to travel and H is the heuristic value. For source, f of s is equal to 0 plus 5 is equal to 5. That is, we have entered the source. Now moving on from S, we have other two vertices. Now the cost of S to A is 1 plus 4 is equal to 5. And the cost for S to B is 2 plus 5 is equal to 7. So now S to A is the shortest path. And we choose S to A. Now moving on here, the paths from A and B to the destination will be calculated now. So the total for the paths SAE comes up to 14. And the path for SBE comes up to 7. Now we choose the path SBE as it is the shortest one. So after calculation, we have found that B has given the least path. So we have changed our least path to SBE and reached the destination. And this is how we use the formula to find the optimal path. Let's see an algorithm to understand this example. You have two lists here, which are open and closed list. Open list is the node that we are currently visiting and are on. And the closed list over here is what we have not visited. Okay, let me explain now. First, we add the start node to the list. So for all the neighboring nodes to the start node, we will find out which is the least cost of f. So once we have done that, we switch over to the closed list. Now for all the nodes that are adjacent to the current node, we have to find if there is a node which is reachable. If it is not reachable, you have to just ignore it. If a node is reachable, then check if it is on the open list. If it is not, move it to the open list and calculate f of g and h. Now if a node is on the open list, make sure to check if the path is lesser than the path that we are currently on. If so, change over to that path. Now you stop working when you find the destination, or you cannot find the destination going through all the possible points in a given graph or map. And remember, A star algorithm returns the path which occurred first, and it does not search for all the remaining paths. And the efficiency of A star algorithm depends on the quality of heuristic. And moreover, A star algorithm expands all the nodes which satisfy the condition f of n. The A star search algorithm is said to be optimal if it follows the two conditions. The first condition required for optimality is that h of n should be admissibly heuristic for A star tree search. The second required condition is consistency for only A star graph search. That is, the tree search version of A star is optimal if h of n is admissible, while the graph search version is optimal if h of n is consistent. If the heuristic function is admissible, then A star tree search will always find the least cost path. And the A star algorithm is said to be complete if the branching factor is finite and the cost at every action is fixed. The time and space complexity of this algorithm is b to the power d. That is, the number of nodes expanded is exponential to the depth of the solution. B is the branching factor and d is depth. And next we move on to the last topic, which is applications of search algorithm. Search algorithms are used in solving real-life vehicle routing problems, which are optimization problems. And this problem establishes the optimal series of routes that should be taken by the vehicle to deliver the customers. This is a combinatorial optimization problem that seeks to minimize the cost and time taken to reach the given destination. So these search algorithms are used to search for the best solution. In healthcare systems, the provision of healthcare services for 24 hours a day requires the full-time presence of nurses, and nurses cannot work without rest. So scheduling is done to ensure the shifts are allocated optimally to enhance the productivity. So the search algorithms are applied in this case to solve the nurse scheduling problems. Search algorithms are also used to retrieve information or records from databases. The desired record is configured as the desired state. The algorithm searches in the search space and goal tests are made until the desired record is found. Additionally, these algorithms are used in optimization of industrial processes. A good example is a situation of chemical reaction. So in this case, the procedure may require changing some parameters like temperature or pressure, serves as an excellent illustration. So once the initial and desired states have been established, a sequence of operation is carried out in order to achieve the desired state. So with this, we have come to the end of the session. Thank you so much for watching.